And you're watching on YouTube. So let's understand the last question of weekly contest 454 that we have seen in the contest, right? So I have not uploaded the video, so I thought to make this video on this topic. Okay, so the question is saying that we have given 3585, right? The question number 3585 from the Leetcode. We have to find the weighted median node in a tree. So what we have given? We have given an integer n, an undirected graph, right? A weighted tree rooted at node 0 means we have given an integer n and an undirected weighted tree root at node 0 rooted, okay, at node 0 with n nodes, that is number from 0 to n minus 1, right? So this is represented by 2D edges of length n minus 1, where the edge at I is, we have given u, v and w. That indicates an edge from you can say node u to v with weight w. So the weighted median node is defined as the first node x on the path from u to v. So if we are moving from u to v, so the first node that will come is x, right? That is called median, right? Such that the sum of the edge weight from ui to x is greater than or equal to the half of the total path weight. So let's suppose you are going from Bangalore to Delhi, right? So in the middle, let's suppose something is coming, let's say Nagpur or something, right? So that is we call a median, right? Median node. So if we are going from Bangalore to Delhi, so the first node will come what? Let's suppose is coming Nagpur, right? So we'll say the Nagpur node is the is the first node, right, from the Bangalore to Bangalore to Delhi, right, in between that. So we'll take the sum of a's weight from ui to x, means x will be the first node, okay? So the sum of a's weight from ui to x is greater than or equal to half of the total weight path, right? It becomes the median inside, means we can say half of the path, right? So that is called total weight by 2, you can say. So you are given 2D integer array that is called queries, right? And the queries is like u and v, and we have to determine the weighted median node along with the path from u to v. So we have to return an array answers, where answer at j is the node index of the weighted median for query j, right? So ij, this is given, just forget that, just think about the first node itself and then and the elements that we have given at the particular index, right? And you can say not, you can also consider ss at I is ui, vi and wi like that, okay? So just think the concept, what concept is saying that, okay? So couple of examples we have given in this, so you can go through these examples, right? We'll talk much in this video, okay? So these are the examples given. We have given constraints, we have given, you can pause and go through the constraints. So what is the problem behind the, what is the intuition behind the problem, right? So we have given a weighted tree and we have been asked to find the first node on the path from u to v, where the total weight from u reaches at least half of the total weight. Means we have given a weighted tree and we have to find what? The first node on the path from the u to v, where the total weight from u reaches at least half of the total weight, right? It is, we can say, middle, okay? So imagine you were walking from one city to another and the road has varying distance between cities, right? So you want to stop at the first city where you have covered at least half of the total journey, right? You can say in the kilometer, right? Not the halfway. So when we are going from here Bangalore to Delhi, right? So in between the Nagpur is coming, right? So we can consider this is the first stop we will take, and because we have covered the half of the pathway, half of the journey, right? So not the halfway through the cities, right? A number of cities, right? But our total journey half, right? Half of the total journey. Let's say the path is, we are going u to v. U is Bangalore, v is Delhi, and x is what? Nagpur, right? So an is weighted on the path are, let's suppose 3, 5, 2 and 4, right? If you calculate all these path weight, right? So 3 plus 5 is 8, 2 10 and 4 14. So total weight will become 14, right? So we need the first node x where the weight from u to x is greater than equal to 7, right? And we don't care how far we have gone in the number of steps, only the accumulated age weight we will consider. Okay, so what is our approach? Our approach to build the tree, right? First of all, we'll build the tree. In the very first step, we'll build the tree. How we'll build that we'll discuss later on. Just think that what is our approach, right? So the very first step we will do, build the steps, build the tree, and then we'll pre-process the DFS. You know how to how to do the DFS, right? So these are the prerequisites to understand the problem, okay, and write the code, because this is a very tough problem, right? And I'm making it very easy so that any beginner or any student can pause the video, just he can go how to build the tree, he can understand how to do DFS, right? And then what is LCA, and how we'll find the binary search, right? How, what is the binary lifting, right? You just pause this video and you can go through that, right? And you will understand very clearly, right? Still, if you want, right, just continue and don't worry, I'm covering everything here. Okay, so first of all, in the very first step, what we will do, we'll build the tree, right? In the very first step, then we'll process the you can say with the DFS, right? And then in the step 3, for each query u to v, right, when we'll process each query that is given from u to v, right? So step sub step will take from the step 3, right? We'll find LC of u and v. Then we'll take the step, compute the total path weight, and then we'll do the binary search on the path. Then finally we'll use the binary lifting to move up, right? How, what are these things are there, what the steps are there, that we'll talk much more further. Just think the problem statement. So let's start simple. What you have given, so we are given what, an undirected tree with n nodes, means the number from 0 to n minus 1 we have given, because it's tree, so we can say number is from 0 to n minus 1. So each edge has a weight, right? Each edge, because it is a weighted tree, right? A list of queries we have also given, so each asking what is the first node on the path from u to v, where the total weight from u to that node is at least half of the total journey, or total weight from u to v, right? So we call this node the weighted median, right? And so if we'll take the very first step, right, understand the tree, what is the tree is given. Let's suppose this is the tree we have given, right? So a tree is a you can say connected graph, and has no cycle, exactly n minus 1 edges, right? So if you build the tree, it will look like this, right? Because the graph is saying that it is connected, means each node is connected with each other, right? There can be many cities. Let's suppose if I am starting from 3 to 2, right? Let's suppose this is Bangalore and this is Delhi. So there can be many cities that is connected with each other, right? And so it is saying that the graph is connected, right? So if graph is connected, right, means each city is connected in this path. Okay, and so we can also say there is no cycle, right? Exactly n minus 1 as we have given, right? So if we'll talk about the edge weight, right? So from 0 to 1, right? From 0 to 1 we have what, 3 weight we have given. 0 to 2 we have given 5, 1 to 3 we have given 2, and 1 to 4 we have 1. So these are the weight we have given in each edge. You have to just consider, it is not given, just assume that we have given, right? So as we know that these weights we have given, right, and this is the edge we have given. So what we need to do, what is the weight median, right? Let's say the query is 3 2, right? Means we want a path from 3 1 0 2, means we want to go from here 3, then 1, then 0, then 2, right? So weight from weight will come from what, 3 to 1 is what, see here, 3 to 1, 3 to 1 is 2, right? So like that we'll consider, means the, if we'll check 3 to 1 is 2, or 1 to 3 is 2, 1 to 0 is 3, 0 to 2 is 5, right? If we will add all of these, total weight is become what, 10, half is become what, 5. Now walk from 3 to 1, the weight is what, 2, then 1 to 0, total is 5, right? Become half become, right? So the answer of the node is 0, if we'll go from here to here and then from here to here, right? So when we'll reach from when we'll start from 3, then we'll go 1 and then we'll go 0. So when we'll reach to this 0, this will become your half of the total journey, right? And this is become your median, right? Weighted median. What do we need to solve this, right? What we need to solve this problem? To solve this very efficiently, right, especially for many queries, what we need LCA, lowest common ancestor. We have to find the meeting point of U and V, means two city, U and V cities, right, you can say, or two nodes, we can say, of a tree, right? Means this is the meeting point, and so this is called lowest common ancestor, LCA. This is a really a problem of subproblems, right? Because LCA itself is a problem statement. You know how to find the LCA. It's a Leetcode problem. Binary lifting is a Leetcode problem. Distance from the root is also a Leetcode problem. Then a binary search itself a problem, right? Means the 4 problem statements is added in this problem. So this is very important problem, how Google or any top MNCs are asking, right? Means top product based company like Fang is asking. I'm just teaching for the Fang, right? So I'll talk only about the Fangs. I don't care with any other companies. Just think about the LCA, binary lifting, distance from the root, and binary search. So these top concept we have in this problem statement, and that is why I'm very excited to teach you in the depth. Okay, so just think that if we want to solve this problem, what are the things we required? We require to understand the lowest common ancestor, binary lifting, distance from the root, and binary search. Why will we use the LCA? Because we know that we have to find a meeting point from two cities, between the two cities, or you can say U and V nodes. Then we have binary lifting, means we have to find the ancestors quickly, right? So if there is some ancestor is there, right? So we have to find that. So to find the ancestor very quickly, we have to use the binary lifting, right? I'll cover in another videos. I think I have uploaded almost the 4 videos of this, but still if you not able to find, I'll try to find, I'll bring in the you can say the comment, or I'll create another videos where we will talk about more in these topics, right? Separate problems are there from the Leetcode, so I'll talk about that problem. If you're really consistent in this channel, right, so you will see all the video coming on the way it is, if it is required, right? So I'll keep posting the video, don't worry. Then we have binary lifting, means we have to find the ancestor very quickly. Then we have distance, that is from the root, means if we want to find the path width, right, means we have to use the distances from the root. Then we'll use the binary search. You know what is the use of binary search? Means if you want to find the median node on the path, right, we can use a searching technique that is called binary search, because binary search it divides the problem into half, right? And then sub problem is also get divided until the search is not completed. Okay, then we'll go for the step 4, that is called pre-processing of the tree, right? Means we will run the DFS from the root, right? We'll first of all we'll set up what we can say, we'll set up the array, right? Means how far each node is from, and then we'll set up the distance, means what is the total weight from the root to the each node, and then we'll set up what node and then j. So 2 to the power j parent of each node for the binary lifting, right? And this is an idea like how to prepare the way, right? Means LCA will take how much it will take the you can say time complexity, right? So whenever you are writing the code, right, your idea should be generated, your mind should be like lightening, the bulb should be up in your mind. It should not should be when we are seeing the question, you should not be in the sleeping mode, or you cannot see you're not thinking of what is the concept, what is the time complexity. You think about the time complexity while writing the code, what is the approach, what is the idea is there, right? So the idea will give you a preparation of the time complexity, and then you will write the code, right? So that time you will think that the get LCA in O of n log time, right, and the lift node upward efficiently, and then we'll use a compute distance between any two nodes, right? So these are the prerequisites. We will set up this, right? Means we need the depth array, distance array, and up array, right? So when we'll do up, we'll use node and j, right? So that is for binary lifting, right, that we'll do. So let's suppose we have answering a query. Let's suppose the query we have going to ask, right? So multiple queries are there. So for each query, first of all, we'll find a LCA, U and V. So LCA will take U and V, two nodes it will take, right? And then we'll find the LCA of U and V. Then in step 2, we'll compute the total path. How we'll find the total path? We will use total equal to distance U plus distance V. Distance at U plus distance at V will get the distance, right? And then we'll do minus 2 into distance at LCA, right? What is the LCA of the LCA itself will have some value, so because we will calculate the LCA right here, and we will pass the dist at it, right? And you will get the total. Then we'll take the half in total plus 1 by 2, you will get the total, you will get the half. And then we'll use binary search to find the first node X on the path from U to V, such that the distance U to X is greater than equal to half, right? And then we'll use a helper method that is called get node and m node, and you can say U and V. We'll use the some steps, and then we'll use LCA, right? And we'll do binary search on the path. How we are going to do binary search? Let's suppose we'll take the low is 0, high will take the path length, right? And we'll do what? Low is until we will move this code, right? It will run this code until the low is less than equal to high. You know how to do the binary search, right? I will not talk much about this, but you will find the X, right? This is the you can say median path, right? You can say median point, you can say the first node, right? That X, we know that. So you will get that X, you will get that D, you will check if it is greater than equal to half, save this X, right? And we'll say high equal to mid minus 1, else mid plus 1 will become the low, right? Like this, you know the binary search, right? I will not talk much about the binary search because the video will become more lengthy. Okay, now think about the final point. What we will need to do means, first of all, we'll build a tree using the adjacency list. Then we'll do the DFS to populate the depth and the distance, and then we'll use the binary lifting to move up the tree, and then we'll use the binary search to find the median node, and we'll convert back to 0 node. So this is the final point that we are going to do, right? So if we'll talk about the assignment, right, what before writing the code, what we should do, right? So the first task is to implement the DFS to populate the depth and dist. Then we'll implement the binary lifting table. Then we'll write that LCA. Then we'll write the node method, right? And then we'll find each query. We'll use the binary search to find the median node, right? And if we'll talk about the example, how it's work, right? Let's understand the example. So input example we have given n equal to 2, and SS we have given 0 1 7, queries we have given what 1 0 0 1, and output is 0 1. So this is the first example that we have given, like 0 node we have given and 1 node we have given, and the distance between this, the weight is given 7. So let's break down the example 1 and understand how exactly we find the weighted node, weighted median node, right? So let's suppose n equal to 2 means we have given two nodes 0 and 1, as you can see here, right? Means the edges we have given 0 1 7 means there is one edge between node 0 and node 1 with the weight 7, right? And the queries we have given what 1 0 and 0 1, right? So we are asked for each query what is the weighted median node, right? Means if the, let's also understand the rule, right? What is the rule? Weighted median node, what is the rule? So from path, if you are moving from U to V, we have to find the first node such that the sum of the edge weight from U to V node is half, greater than equal to half of the total path. So this concept, never forget that, to find the weighted median node. Then query we have given two queries, we have given 1 0 and 0 1, right? So let's suppose when we are moving from 1 0 means we are talking about from 0 to 1, and another queries we have given 1 to 0, right? Like that we have given. Okay, so when we want to go from 1 to 0, right, path is what 1 to 0, then the weight is 7, so total path is 7. If we'll take the selling value by 2, right, it will come what 4 7 3.5, right? It will come 4. So we'll start from the node 1, we'll walk towards 0, right? Because we are moving from 1 to 0, because we are starting from here and we'll moving like this side, right? Like that. And so the distance from 1 is 0, because this doesn't meet the requirement, so we'll discard it and we'll say distance from 1 to 0 is 7. This meets our requirement, right? And so we'll say answer is 0. Now query 0 to 1, right? Let's suppose we are going the query from 0 to 1, right? Like this direction will go, this direction. Okay, so in this case we want to go from 0 to 1, right? So path is from 0 to 1, age is 7, age weight is 7, then total path is 7, selling value 7 by 2 is equal to 4, we'll start from 0, we'll walk towards the 1, right? When we walk towards the 1 means 0 to 0, it become what? 0. And it will become, the distance from 0 to 1 becomes 7. It also meets the requirement. So there is 0 and there is 1, the right answer. So if you summarize this, the query 1 gives what? 1 0, right? And it start from what? This is the weight, so 1 weight 0, right? Means 1 if you are going from 1 to 0, the weight is coming 7, right? So very first node, where the distance is greater than equal to 0, greater than equal to 4 is what? 0, right? And when we talk about the query at 2, 0 to 1 means we are going from 0 to 1, right? This is distance. The first node where the distance is greater than equal to 4 is 1. So we are seeing that it is coming 0, this is coming 1, right? And so with the final output will come 0 to 1, right? So this is 0 and this is 1. So output is coming 0 1, right? So if you write the code, what needs to do? So first of all, build the tree. We'll use the binaries, we will use the adjacency list. So for each node, we'll store the neighbor nodes and as you will write adjacency. You know how to write the adjacency. At adjacency list at u will add the its neighbor, right? So it will take all the neighbor nodes here, right? Means let's suppose v and w is there, right? Means we want to add that you have a neighbor v, right? You node u have neighbor v and its weight is w. Similarly, node v has neighbor u and the weight is w, because it is unidirectional, right? Undirected, right? If it is directed, we will take only one path. Then we'll use pre-process with the DFS, right? Let's do the DFS from the root node 0. Node will take 0, right? So we'll use depth node, we'll dist at node, and we'll use setup node j, right? That we have discussed already. Okay. For each query, we'll use u to v. We need to find the first node x on the path u to v, and where the weight will become what? Far is greater than equal to half, right? So in the very first step, right, we will make a query, right? We'll go for the each query and we'll find the LCA. Then how we are going to find the LCA, that we'll talk. Then we'll compute the total path, right? How we are going to find the total path, and we'll divide the half, you will get the half, right? We'll take the LCA, we'll store the LCA also. Then we'll do the binary search on the path, right? You know how to do the binary search. Just pause this and go through. Then we'll use the binary lifting to move, right? Means if you want to move, lift the node and the steps, you just need to pass the node and s steps, right? It will lift up, right? So we want to what is the use of binary lifting? So we can use to find the any ancestor of the node and any node along the u to v path, right? That is the purpose. We will use the lifting. Okay. And the time complexity will take pre-processing and log n, and for each query will take log n into log n due to the binary search plus binary lifting, and it will efficiently handle 10 to the power 5, right? So let's continue and understand the code. Okay, so summary of the flow is to first build the tree, make the DFS for the dist and depth, and these variables you define, and for each query first find the LCA of u and v, and then you'll compute the total weight and then find the half. Then you will do the binary search for the first node x, and where the dist at u and v is greater than or equal to half, right? I have tried to cover everything in this 20 minutes. Let's understand the code. Okay, still if you understand that I am able to I am able to write the code, that's very good. You pause this video, go through this, and thank you for seeing the video till now. Let's understand the code. Okay, also like and subscribe the channel. Let's understand the code now. Okay, so now understand the code. Okay, so first of all, we'll define some class variables, right? So these class variables we have to define. Why? Let's suppose we'll go from the first line, right? So first of all, we'll define adjacency list. So this is an adjacency list. You know the adjacency list, right? So we'll create this adjacency list like this, because the list will contain, this is a type of list, and each list will contain a set of nodes, right? So the set of nodes will be in where? In a array, right? So in array form, and that array the list of array is there, and each node will contain a set of neighbor nodes, right? So each node has a list of what? Neighbor and its weight, right? So that we will store, right? means we want to add for each node, we can say what will take adjacency list at u contains a list of what? Int v and w, right? Remember that we have to do, right? Like this, the line is here, right? So if we want to add what? For each element, right? Each nodes, right? Each node is there, we can say, or each cities, right? So each node contains what? U, having what? A list of integer, and that list of integer contain u and w, sorry, meaning an is from u to v with weight w, right? And so we'll create what? First of all, the adjacency list. So this is an adjacency list, and for each adjacency at u, you can say, will store what? A set of you can say a list of node and its weight, means an is from u to v with w, right? That we can say means weight. So that is why we'll create the adjacency list. I hope you understand, right? Because without adjacency list you cannot do anything. Then we'll take another variable that is called depth. What is for this depth? So this depth method will store how deep each node is from the root that is used from for you can say LCA and the path distance, right? So you can say the depth of each node in the tree for binary lifting, right? And so we'll use this depth, right? So let's suppose this will store what? Many nodes, right? Each nodes it will store, right? And so each nodes contains its depth. So if you'll pass depth at a node, you will get the some results. Let's suppose here you can see here, right? Depth at 1, right? We are getting what? 1, because at 1 we'll consider 1, because we are starting the DFS from node 1 itself, so which is node 0 in the original input, right? So we can say its depth is 1. So for the parent node, the depth will become what? The root node become the depth is 1, right? You understand, right? So we'll define this variable. Then we'll take the third variable that is called dist. So this dist will store the total is weight from root to node I, right? So whenever we want to store the weight from, let's suppose root reach a parent node, and then we'll come to the child node, right? Any node is there. So node I, let's suppose we'll say I is any node of the you can say tree, that will store at where? There, right? So now think, we will store what? Let's suppose max depth, right? So max depth to support the binary lifting is, this will become what? 20 to the power 20, and 10 to the power is should be greater than equal to 10 to the power 5, right? So this is called max depth that will support binary lifting. Okay, so we'll take the log 20 means maximum level of binary lifting, since 2 to the power 20 is greater than 10 to the power 5. So this is safe for the most tree with less than 10 to the power 5, right? We can say that. Then will we use what? The up 2D array, right? Means we will use binary lifting table. This is called binary lifting table. Means up at what? I and j will store at I and j. There is two binary, right? So in the binary you can say 2D array. So in the 2D array, right, or you can say binary lifting table, so there will be two I and j will be there, two indexes there, right, for each cell. Means 2 to the power j is the ancestor of node I. If we'll write I and this will write what? J, means 2 to the power j, jth ancestor of node I. Okay, and that is why we are writing here. I hope you understand this class variable. What is the purpose of writing this class variable? If you are not understanding this class variable, it will be a little difficult. So you pause this video, go through what is the each of them meaning, right? And that is why I have written the comment here. You go through and understand it. Now think about you can say the main method. So what is our main method? Our main method is to find median, right? So this we have given int n, we have given ages, we have given, and queries we have given. If you go through the you can say questions, right, you can see here we have given what? Three things we have given. Node n we have given, then we have given ages we have given, and then we have query we have given, right? We have given these things. Okay, so what I will do, what we will do, right, we'll pass all these three variables, and the quest or the by default it is already given, so no need to worry about it. Means the you just match the example also. Okay, so just think that we have given n, age, and queries, right? N is the number of node, ages, and queries, you know that, right? So n will become what? Number of nodes. Ages become what? Age list, and query will have what? Each query ask to find the weighted median node between two nodes, correct? Now in the very first step, what we should do, we should initialize all the class variables, right, that we have used, right? Means initialize the structures of the objects, right, you can say. Okay, so all these variables we will initialize here in the very first step, right? So let's suppose the urgency list, we will take n+1 its size, right? Depth will take what? n+1. List will take n+1. Up will take n+1 and log 20, because maximum will take 2 to the power 20, right? If it is 2 to the power 20 is greater than 10 to the power 5, right? So max depth we have to support 20 only, right? So we'll use that one. Okay, and that is why we have taken 20. Now for all the nodes, right, we will at each node, right, urgency at each node, there should be a, you can say, list of nodes, and so we have to initialize like this, so that urgency at I, we will add what? Nothing but some nodes we will add, right? Each nodes we will add. What is this node? So its a nodes type is what? If this diamond bracket will not say anything, you have to go to the when it defines, right? So it will store a array. So whenever we'll add on this urgency list, we'll use the add method, but we will not take one element, we'll store a combination of two things, each array, right? So each array contains v and w, right? Will store means we'll pass the another node and its weight from the u, right? I hope you understand. Still, if you have doubt, please ping me in the comment box. Okay, now this is done, right? Now in the next step, very next step, what we will do, you will use the building the graph, right? Actually now the steps start, but before that you should understand how the code works, right? Now understand how we are going to build the graph, right? So first of all, we'll initialize everything, right? We'll initialize each of them, and then we'll initialize each list in the urgency array, right? That we'll do here, right? Once it is done, then we will write the graph. Okay, so how we are going to build the graph? So for each graph, right, for each edges, we'll traverse for the edges, right? Each edges, you will get u at 0 and v at 1, right? And w, you know. So you as at 0, you will get u, and you write just use +1, because we are using one indexed for simplicity, right? It was 0 indexed because it is what? 0 to n. If you remember, it is from what? 0 to n-1, but we are trying to convert it into the one index, right? To one index, you have to do whatever the value is coming, you just do +1. It will become what? First one index, 0 index to 1 index. Understand? I hope you understand these things. Now we have converted the, you can say, 0 based is endpoint to 1 based, right? And then we have got it. So now you know the w, right? So w is the weight of the s, right? So what we will do, we'll do s at u, we will add what? As we will add new v and w, right? Similarly we'll do for v, and then we will reverse the w, v, u, right? Means we are doing what? Since why we are doing this? Since the tree is undirected, there is no direction there, so we'll use the we will do first time for u to v and then v to u, right? And each weight we will add here, right? Since the tree is undirected and the s having both side, right? We have to add the s's in both ways, this way to this way. Okay, left way to right way. Now in the third step, what we need to do? Okay, so we have to understand what in the step we will use what, the DFS, right? Means we will do DFS to set the depth, distances and ancestors, right? So first of all, we'll define depth at 1 equal to 1, and then we'll write what, DFS at 1 and 0. It means we want to start the DFS from node 1, right? And original node is 0. Okay, so we'll set the path, right? So we'll set the depth, you can say, and the distance from the root, right? And so we will use what, 1 comma 0. So first of all, we'll set the depth equal to 1, right? Means we'll set the depth and its distance, right? And then we'll write the DFS what, 1 0. So we'll fill the, you can say, distance. We'll fill the uplifting will do. Means we want to do DFS 1 0. It means up I is I and 0 equal to parent I, right? That we will do. Understand how we are going to do? Understand here. Now we are doing binary uplifting, right? So when we'll start for each j, we'll go for each I, right? So you know, up at I, right? And here it will go what, j minus 1, right? Means for each log, right, we'll move here. Let's suppose if we'll fill what, depth at up at I, right, and we'll pass what, 0. Okay, because it is 1, the first time it is 1, so it will go what, 0. So up at I and 0, right? I is what, 1, means 1 0. This is become what, parent at I. Okay, so for that we'll take P, right, and we'll store how, if parent is not equal to what, 0, and its value is, if it is not equal to 0, means we'll use what, P and j minus 1, and we'll store 0. Okay, so like this we will do the binary lifting, and we'll construct the what, up. So you will get the 2D binary lifting table will be constructed. So till now we just initialize everything. Now the final things begins, right? So you have one doubt till now. Let's suppose I'll convert this what is this DFS, right? So DFS is a DFS function, or you can say method, that will record the immediate parent for binary lifting, right? Let's suppose I'll show you DFS method first. Let's suppose this is your DFS method, right? So what we will do, we'll pass node and its distance. Means we want to populate the depth, distance and first ancestor, right? The first ancestor we will go up at node and 0, right? So you will get what, we'll store this value first, up node at node and 0, it will go what, par, right, the distance. And then we'll use for all the adjacency list, will get what is the next is there, what is the W is there, right? We will set all this value like this, right? Depth at next, depth plus node means next, what is the next node, from the parent node to the next node, you will define the depth. Each depth will added plus 1, right? And its dist at this become what, plus W will get added. And then we'll go for the next node and the DFS. You know the DFS, right? DFS is very easy, no need to explain much. Just pause this video and go through this. Okay, so I hope you understand till now, right? Means what we need to do in the DFS. Now we will do here, right? So what we need to do in the DFS, for each child node and the weight of the edge from node to next, we were updating the depth, distance, and then we will recursing the deeper into the tree. Means DFS will keep from the parent, it will keep down to the child, right? And then we will recurse the deeper into the tree. Now understand the final process, right? How to process the each query. So until you build the binary lifting, right, you cannot do anything, right? So till here you have to do everything, and then you will process the query. So for each query, you know the query queue, and will define the answer and will finally return the answer, right? So for each query, we'll go from I0 to a query, and for each query we'll get U and V will get. Then we'll find the LCA. You know how to find the LCA, right? Let's go and see the how to find the LCA. Okay, so this is the method to find the LCA. Okay, you pause this video and go through how to find the LCA. Okay, we'll cover later. Okay, then you will compute the weight, total weight from U to V. Means total weight is there, U and distance, and minus 2 into dist at this, right? That we have discussed. So we will find the total, then we will find the tar, right? So you will do plus 1 by 2. This is become your half, right? This is your half as a tar, right? So we'll take this, and then we'll do binary search, right? Then you will get the path length, and you have the low and high. So low will become step 0, and then we will have the high is path length, and by default you will take x equal to v, default to v in case of binary search field, right? Then we will do the binary search. You know how to do the binary search, right? And you will update the answer at I is x minus 1, right? We are converting back from you can say converting back to 1 index to 0 index, right? And once everything is done, you will return answer. Okay, means what we are trying to do here, right? So first of all, what we need to do, we need to define the queries and the answer, and this answer we have to update. So for each query we will get the U and V, right? We are converting convert query to 1 based, right? You just do plus 1, right? And then you will find what? LCA, means you find the lowest common ancestor of U and V, and you will get what? Total W. And tar, means we want to calculate total weight of the path from U to V, and then the target weight we will find. What is the target weight? Is half. So we'll do total weight plus 1 by 2. You will get the half, right? That is the target weight, and we are doing round up. We can do that. Then you need these things to do the binary search. Till that, no need to discuss much, right? You just need to find what? Total steps on the path from U to V. You have to just update the path, right? And once you will get the weight total, right, you will get the total weight, right? You will keep update, you will keep checking. If the weight is greater than equal to this, means we find so the candidate found, right? And you just update mid minus 1 high, otherwise n plus 1. You go deeper, right? Means we start from 0 to the path length, and default node is will take V. Okay, then you will do, you know, the binary search, right? So in the binary search, the node is at mid, right? Node will become at what? At mid. So for that you have to find the mid, right? So mid will start from U to V, right? And so that you will find the weight. You know that how to compute the distance from U to the node, right? And then you will calculate the weight, right? You know how to calculate the weight. You just check with that if it is greater than equal to target. We found that, right? Otherwise you update the low, right? Low become what? Mid plus 1, means we are going deeper, right? If the weight satisfy the target, it's a candidate search, right? If the candidate search, otherwise we'll go deeper, right? And then we'll convert back to 0 index because we have updated to 1 index. Now understand the LCA function, right? Where is the LCA function here? Okay, so in the LCA function, what we are going, we want to ensure U is deeper, U and V, right? So we have to find the LCA using binary lifting, right? So now how we are going to do that, right? Let's suppose you have the, you will just check this, right? Means U should be deeper, right? And for that you will get the lift of U, right? You will get, and you will just check, right? These things you will return it, right? It means if let's suppose lift u up until it's the same depth as v, right? If it is equal to this, it means we will return, right? Otherwise we'll keep digging this, right? Means we'll go for all the you can say both will do lifting. We'll lift both together until their ancestor match, right? Once this is match, you will return it, right? Okay. So we can also say why it is required, because efficiently will move the node by k steps, right? And for that we have to write it. Okay. Then understand this method. It's very big code, right? So you have to understand. Now understand the getMn node, right? So the getMn node will take what? You will find the kth node from the path u to v, right? So in this case, we just want to return the node from k steps from u towards v, and then we'll go up from u if it is within its part, right? Else we'll go backward from u. You can say v from we just want to go backward from v and will up towards LCA, right? And this is our purpose. So we are going up from v backward, right? I hope you understand, right? Till that, what is the purpose is there? We just want to build the tree using urgency list. We want to pre-process the depth, right? And then we are building the, it is called binary lifting. Yes, these are the steps you have to follow, right? For each query, we just find the LCA, then we'll use the binary search to find the first node where weight should be weight from u should be greater than equal to half of the total, and then we'll use the binary lifting to work the path efficiently. Okay, I hope you understand, guys. I suppose that you understood till now. If you still have any doubt, please ping me in the comment box. I'll push this code into the comment. Thank you for watching this video.
Thank you guys. Thank you for watching this video. If you found this video helpful, please like, subscribe, and let us know what you want to learn next in the comment below. And thank you for watching this video.